Hey everybody. Last time we were talking about the best theory that we have today to explain the formation of our solar system. It's called the nebular theory, right? And the nebular theory works great, right? The nebular theory basically says if you take a nebula, yeah, you take a cloud of gas and dust and you let gravity and motion and heat do its thing, and if you give it a couple million years, you end up with a solar system like ours, right? And so the nebula theory isn't based on anything like terribly outlandish. It's just take the basic forces of nature, throw them together, and you would expect a solar system like ours, with a sun and terrestrial planets near the sun and Jovian planets far from the sun. There you go, right? Um, and so the nebula theory works great at explaining our solar system because it was designed to explain our solar system. And for the first several decades, the planets around our sun were the only planets that we knew about. And so you could sit back and say, well, okay, we've still got to work out the details, but by and large, we've got planet formation figured out. Here's the nebula theory, here's how planets form. But in the last almost 30 years, we've started finding planets around other stars. And so what are these other planets like? What are these other planetary systems like? Are these exoplanets well explained by the nebula theory? And the answer is sometimes yes and sometimes no. Are they totally expected, or are they wildly weird? And the answer is sometimes one and sometimes the other. So if we're going to understand how all planets form, not just the planets in our solar system, then we need to look at all the planets that we're finding. And so let's do that. How do we find planets orbiting around other stars? And, okay, a little bit of background, right? A little bit of basics. Let's refresh our memories here, right? A star is a giant ball of hydrogen and helium. It is at temperatures of thousands of Kelvin, and the core is hot enough to take hydrogen and fuse those atoms together and make even heavier elements, and that's how a star stays hot and emitting its own light for millions or billions of years, depending on the mass of the star. A planet is minuscule by comparison, right? A planet is much smaller. It has much cooler surface temperatures. A planet only has a temperature of a few hundred Kelvin. And since it's only that hot, the peak in its blackbody spectrum is mostly in the infrared. And so a planet does give off light, but it's mostly infrared. If you're looking at planets in the visible spectrum, they're not radiating their own light. They're just reflecting the light from their parent stars. And so consequently, when you look at planets, they're very hard to see. I mean, imagine you're an alien looking at our sun, and you're trying to find planets around the sun, right? I mean, obviously these distances are not accurate, but the sizes are close, right? So you've got, if you're an alien pointing your telescope at the sun, you're not going to be able to see these planets around the sun because the light from the sun is going to overwhelm the light that you're seeing from the planets, right? The planets are going to get lost in the glare of the sun. All you're going to see is the sun. And so we here on Earth, we have the same problem. If you're pointing your telescope at a star, you're not just going to be able to take a picture of a star and see the planets around it. The planets are much less bright, much smaller, much lower in apparent magnitude. Much lower in apparent magnitude. You can't just take a picture of a star and see the planets around it. So what we have to do, the reason why we're able to find these exoplanets is by looking for them indirectly, right? Most of the planets that we have found, were found by indirect detection. Basically, what that means is you're studying the star, and by analyzing the star, you're able to infer the existence of the planets around them, even though you can't see the planets themselves. There's a lot of different methods for doing this. There's a lot of different methods for detecting exoplanets. That, by the way, is the term for them. You've seen this on the homework, but what an exoplanet is it's short for extrasolar planet, right? A planet that is beyond the solar system. So exoplanets are alien planets orbiting around other stars, not the planets in our own solar system. All right, just wanted to make that clear. There's lots and lots of different methods for trying to find these exoplanets. We're going to focus on three. The transit method and the Doppler method are the two most productive methods. They're the methods that have found the most planets so far. The coronagraph method is actually a direct detection. Using a coronagraph, you can take a picture of the planet themselves. This technology is kind of in its infancy, but this is the future. Right? The transit method and the Doppler method are what we've been using for the last 20, 30 years. Most of the planets have been found using those two methods. The coronagraph is the future, right? The coronagraph is the real cutting edge, and so that's what you're going to be hearing about over the next 5, 10, 20 years. So we're going to talk about coronagraph at the end, even though there isn't any questions on the homework or anything about coronagraphs. We're going to talk about that at the end because that's the new awesome frontier. So, but the transit method and the Doppler method are indirect detections. You're studying the star and inferring that there must be a planet there. All right? So it's a little tricky. It's a little backwards. But it works if you do it right. So how does that work? All right. That's what we're going to talk about here. This lecture is going to start with talking about the transit method, and then the next lecture we'll talk about the Doppler method and the coronagraph method. The Doppler method is also called the radial velocity method, which is that's what it's called in the homework, for reasons that we'll get into in the next lecture. Before we get there, though, I want you to start thinking about strengths and weaknesses. Right? The reason why there are lots and lots of different methods for hunting for exoplanets is that none of these methods is perfect. None of these methods is going to find all the planets that are out there. They all have their pros and cons. They all have their strengths and weaknesses. Some kind of planets are easy to find using a certain method. Some kinds of planets are hard to find. And so as we're going through these different methods, I want you to think about this. Using this method, based on the way this method works, what kinds of planets are you likely to find? What kinds of planets are you unlikely to find? Because that is going to influence the planets that we have found so far. Okay? So, keep this in the back of your mind. Think about what's easy and what's hard to do using these three methods. Okay? And we'll talk about this later on. Okay. First thing, the transit method. All right. A transit is basically a little mini solar eclipse. Right? A transit is what happens when a planet passes in between a star and you here on Earth. So in our solar system, we see transits of Mercury and Venus because Mercury and Venus are closer to the sun than we are. And therefore, every once in a while, every few years, Mercury or Venus will pass directly in between the sun and the Earth, so that what you see is, if you look at the sun, you'll see a little silhouette. You'll see the silhouette of Venus covering up part of the sun. All right? So that's what a transit is. Now, if you point a telescope at another star, the star does not look like this, right? You can't point your telescope at a star and see the disk, the face of the star, because the stars are way too far away, right? When you point your telescope at a star, it just looks like a pinpoint of light. Our telescopes don't have the angular resolution to actually see the size of a star. A star just looks like a pinpoint of light. And so if you can see a planet cover up the star, well, then there you go. You know there's a there's a planet there. But when we take a picture of a star, you're not going to be able to see the silhouette of the planet transiting in front of the star. What you're going to see is, you're going to see the star, you're going to see that pinpoint of light, but it's going to get dimmer for a few hours as that planet partially blocks the star. And then once the transit is over, once the planet has passed in front of the star and then it's gone, then the brightness of the star goes back to normal. That's the smoking gun. That's the telltale sign that there must be a planet there if you see this partial dimming of the star over a few hours. That's the crux. That's really the heart of the transit method here, right? When the planet orbits in between the star and you here on Earth, then the star just looks like a pinpoint of light. But the apparent magnitude of that star, right? Before the transit, the star is its normal apparent magnitude, or partial, or the normal flux. And then the planet blocks the star, and so the brightness dims for a few hours while the planet is transiting in front of the star, and then the transit is over and the star goes back to normal. If you watch a star, and it's normal, 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 dip, 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 normal, 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 bingo, something happened. Something happened there that tells you maybe there's a planet there. I'm pretty sure there's a planet there, because that dimming for a few hours and then the star goes back to normal, what could have caused that star to dim out for a few hours and then go back to normal? I think there's a planet. Right? The shape of that graph really is the telltale sign, right? So if we could, let's make a cartoon here. Let's say, all right, if we could zoom in, if we had a telescope powerful enough to actually get the resolution to see the detail of this transit, what would it look like? Well, you'd see the star, and then there's the planet covering up the star, transit, 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 and then it's over. The star goes back to normal, right? So let's look at this step by step, right? Here's the star, no transit, right? And again, if we're looking at this star with our telescope, all we're going to see is the star. As the planet gets close to the star, again, all we're going to see is the star. The brightness of the star looks totally normal. Then for a little bit, as the planet starts to transit in front of the star is partially being covered up. And therefore, the brightness that we're seeing here on Earth is going to get, as that star gets more and more and more in front of the star, the brightness of that star is going to get dimmer, 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 even dimmer. Then the planet is fully in front of the star. Now 100% of the surface area of the planet is in front of the star. So now we're at maximum coverage. That planet is covering up as much of the star as it can be. And so as long as that planet is in front of the star, then the star is dimming as much as it can this whole time. And then the transit is over. As the planet starts leaving the star, now the brightness of the star is going back to normal, and now it's totally back to normal, and the brightness flattens out. The star's apparent magnitude has gone back to what it normally is. That's your transit, right? You see the transit. You measure the transit by measuring and constructing what's called a light curve, which is just astronomer jargon, right? And a light curve is just an astronomer's term for a graph of brightness versus time. That's it. It's nothing more complicated than that. So that's what we were looking at before. That graph is the light curve. It's a graph of brightness versus time, right? So all you've got to do is do the simplest thing you can do in astronomy. Measure apparent magnitude. Look at the star. How bright does it look? That's the apparent magnitude, right? And then measure the brightness again. How bright does the star look now? How bright does it look now? How bright does it look now? How bright does it look now? Make a series of measurements of apparent magnitude over a period of time, and then make a graph of brightness versus time. And if the brightness of the star changes, if the brightness of the star dips, the way we were seeing a second ago, that might tell you there's a planet there. All right? So let's go through this step by step again and put these two ideas together here. All right? Here's your planet. It's orbiting around the star. All right? There's the dip. Okay, now we're fully in the dip. The transit's happening, and now the transit's going to start going over, and the brightness of the star goes back to normal. Right? There you go. If there were no planet, then the brightness of the star, the apparent magnitude of the star, would be constant. But every once in a while, when that planet transits in between the star and Earth, you see, okay, dip, lower, 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 okay, dip, the bottom of the dip, okay, the bottom of the dip, this maximum coverage, okay, now the transit's going over, and now the transit's over. This is the smoking gun. Right? If you make a light curve, if you measure the brightness of the star over time, and every once in a while, periodically, the brightness just dips like this, and then it goes back to normal, bingo, I bet there's a planet there. Right? Here's what a real light curve looks like in practice. This is the light curve for the star Corot 2, or Corot 2. I forget if it's French or English. But this star has a planet around it. And every time that planet transits in front of the star, it dips for a few hours and then it goes back to normal. Right? So, you know, our cartoon here is oversimplified, obviously, but the real thing doesn't look that different. Okay, so you find a planet around this star using this light curve. Again, remember, you can't actually see the planet. All you're doing is taking a picture of that star and measuring the apparent magnitude. Over and 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 over, right? Just make regular measurements of apparent magnitude over the course of several hours, days, and you construct the light curve, and you say, I'm pretty sure there's a planet there. Now, from the light curve, it's not just enough to say, hey, I found a planet. I mean, that's cool and all, right? It's like, hey, I found a planet. Cool, all right. If this were 20 years ago, that'd be amazing. 20 years ago, it was like, I found a planet. Oh my gosh, it's amazing. It's in the newspapers. Literally, you know, the discovery of a new planet would be in the newspapers. These days, we have found thousands of planets, and so finding a planet is like, you know, yawn, we're all jaded scientists now. It's not just enough to find the planet. Tell me about it. What's the planet like? Well, using this method, we can figure out the size of the exoplanet. The bigger the planet is, right, the bigger the planet is, the more of that starlight is going to get blocked. If more starlight is going to get blocked, then the dip in the light curve is going to be deeper. Right? If this were a smaller planet, then the dip wouldn't be as deep. It would only go down here, let's say, and then it would go back to normal. If you've got a big planet like this, then that big planet is blocking a lot of light, and so the dip in the light curve is deeper. And so from the real data like this, you can say, well, based on the depth of this dip, I can tell you how big the planet is. The time for the transit, how long that planet takes to fully transit across the face of the star, the time, gives you a sense of how fast the planet is moving. If the planet's moving slower, it's going to take more time to transit. And therefore, you can get a sense of the speed of the planet, and therefore, you can measure the period. Right? The orbital period of a planet and the orbital speed of a planet depend on what? What determines how fast a planet orbits around its star? It's the distance, right? So measuring the time for the transit gives you a measure of how far away that planet is orbiting from its parent star. And we'll see that even better here in just a minute. Right? So this is how we can figure out real properties of the stars themselves, or sorry, of the planets themselves. Right? Oh, I just said this, didn't I? Okay. So, yeah. So the depth of the dip tells you the size of the planet, and the width of the dip tells you um, the velocity, the period, the orbital distance, right? All that stuff. Okay, I just said that. All right. Okay. I kept saying a minute ago, if you see a dip, you think, aha, there might be a planet there. How do you know for sure? Right? If you're watching some star and you make a measurement of brightness versus time, and if you see one dip, okay, you think you found a planet. How can you be sure? Well, that dip should happen again. Every time that planet goes around the star one time, it should go, every time that planet orbits the star once, it's going to go between the star and Earth, and that should cause another transit. You should see another dip in the light curve. So every time that planet orbits, you should see dip, dip, dip. And so this is how you can know for sure whether you actually found a planet. If you see one dip, you think, aha, I think I found a planet, but let's keep on watching. And then that planet goes around the star, and then it comes in between the star and the Earth again, and there's another dip. And you think, ah, there's two dips. And those dips are the same size, right? The planet is the same size. So let's wait for one more time. There's another dip. Aha! Now you know for sure. If these dips repeat, and if they repeat with the same frequency, if it's dip, 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 if those dips are the same depth, the same shape, and if they're repeating with the same period, with the same frequency, then you know you found a planet for sure. If a dip just happens once and then never again, maybe it was a fluke. But if there's a planet, right, that planet is going around the star, and every time the planet goes around the star, you should get a dip. So if these dips happen repeatedly, then you know for sure, there's definitely a planet there. I found the planet. Here's what the planet's like. Right? And from these light curves, you can actually read off the period. Right? Because every time the planet goes around the star and in front of you again, you're going to get another dip. So the time from one dip to the next dip, that's the time for the planet to go around the star one time. What do we call the time for a planet to go around a star once? That's the period. So the orbital period can be read right off the light curve. It's just the time from one dip to the next dip. And if this is how you know that you're looking at one planet for sure, because there should be the exact same time period between dip 1, dip 2, and dip 3. Or rather, from dip 1 to dip 2, and the same time period from dip 2 to dip 3, and the same time from dip 3 to dip 4, etc. If you know the period, then we're really off to the races, because you can say, well, the period of a planet's orbit depends on the orbital distance. Or remember Kepler's third laws, right? The orbital period depends on the semi-major axis, which is just the average orbital distance, right? But here, we need to use Newton's version, because Newton's version of Kepler's third law allowed for the mass of the star to be different. And if we're talking about alien planets orbiting around a different star, there's no guarantee that your star is one solar mass. So we need to use the full version here and say, okay, in Newton's version, it's m times p squared equals a cubed, where m is the mass of the star in solar masses, p is the period of that planet's orbit in years, and a is the semi-major axis. It's the orbital distance in astronomical units. And so if you know the mass of the star, which getting the mass of the star isn't that hard. How do you figure out the mass of a star? Use the luminosity, right? If this star is a main sequence star, and I mean, granted, that's a limitation, right? The star has to be a main sequence star, but most stars in the galaxy are main sequence stars, so it's not that much of a limitation, right? Take the luminosity of the star, use it to figure out the mass. Boom, done. Measure the period off the light curve, and you can solve for A. You can solve for the orbital distance. You can't even see the planet, and just from the shape of this graph, you can figure out how far away that planet must be from its parent star. How cool is that? What if there's more than one planet going around the star? Well, if there's more than one planet in this system, then you're going to get different size dips, right? The big planets are going to make deep dips, the small planets are going to make shallow dips. Um, and also, those planets are going to have different orbital periods, and therefore your dips are going to happen at different rates, right? So let's see, the time from the big dip here to the next big dip looks like a shorter period than the distance, or the time rather, from this shallow dip to this shallow dip. So you could look at this graph and go, well, I've got big dips closer together, which means this planet must be a larger planet orbiting closer to the star because it's got a shorter period, so it must be closer to the star. Here I've got a smaller planet orbiting farther from the star. How do I know it's farther from the star? Because it's got a longer period. So you can look at, with this transit method, if you get some complicated looking graph like this, you got to look at it, squint at it, analyze it, and say, match the dips that look the same, right? Here's this planet, this one. This is all one planet. These dips all look the same, and they're happening with a regular period. Boom, boom, boom. So there must be two planets in this system. You can decompose the graph, pick it apart, and say how many planets are there, what are their sizes, what are their periods, and then you can sort of make a model. You can make a drawing for yourself of what does this solar system look like? What does this planetary system look like? How big are the planets? How far away are they? How fast are they moving? All of that from just a graph like this. The transit method is the way that we've discovered most of the exoplanets that we've discovered so far. Right? Overwhelmingly, it has been more productive. Why? Because it's so simple. Right? All you got to do is watch a star and see if its brightness changes. But still, there are some planets that are easier to find and some planets that are harder to find. So think about this, all right? What kind of a planet is going to be easiest to find using the transit method? Well, is a planet going to be easier to find if it's blocking a little bit of light or if it's blocking a lot of light? Well, if it's blocking a lot of light, you're going to see a deeper dip in the light curve. That's going to be easier to see in the data. So the easiest planet to find is going to be one that blocks a lot of light. What kind of a planet blocks a lot of light? A big one, right? So the bigger the planet, the more light it's going to block, the easier it's going to be to see the dip in the data, the dip in the light curve. So big planets are easier to find, small planets are harder to find. All right. What else is going to make a planet easy to find using the transit method? Well, a short period one. Because if a planet is orbiting with a short period, then you're going to see the dips more frequently. You're going to see, when you look at the light curve, you're going to see dip, 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 dip. That's going to stand out. You're going to notice that. Right? And so the easiest planet to find is going to be one with a short period, lots of dips in the same amount of time. And why does a planet have a short period? Because it's orbiting close to the star. A planet with a long period might be hard to find, right? If you've got a planet like Jupiter, right? Jupiter is big. Oops, pardon me. Jupiter is big, right? Jupiter's got a large radius. You'd think, that'd be easy to find. Except that Jupiter is also far from the sun. Jupiter has a period like 11 years, which means if you're an alien looking at the sun trying to find Jupiter, you'll see a dip, you'll see a big dip, because Jupiter's a big planet. But then you've got to wait 11 years to see the next dip. What if you're not watching the sun for 11 straight years? You might miss the next dip, or you may have missed the first dip. You may not find the planet. All right? So if you've got a far away planet, if you've got a planet orbiting far from its star with a really long period, you're not going to see the dips as often, or if at all, and you're not going to find the planet. So the easiest planets to find are going to be big planets close to the star, small planets far away, harder to find. That's the weakness of the transit method. All right. Why have we found so many planets using the transit method. And the main reason that we found so many planets is because of the Kepler Space Telescope. The Kepler telescope was, it's a space telescope off the Earth's surface, out there in space, and Kepler basically had one job. Kepler's job was to stare at one area of the sky and watch it constantly. I'll come back here in a second. Here's what the Kepler field looked like. The Kepler field is this big square in the sky. It's about 8 degrees across. So this big square in the sky in the direction of the constellation Cygnus. There's 4.5 million stars in this field. All right? 4.5 million stars. Of those 4.5 million, about 100,000 of them are bright enough that you can get really good measurements of the apparent magnitude. All right? So the goal, and here's where NASA always exceeds expectations. The goal was, we're going to measure the brightness of those brightest 100,000. Now, actually, they ended up measuring the brightness of about 500,000 stars really well. So they did, this is why they found so many planets, is because they were able to take about 500,000, actually over 500,000 stars every half an hour. Every half an hour, the Kepler telescope took a picture just like this. Every half an hour, 24 hours a day, for 4 years. It took this picture, and then every month they would download the pictures down to Earth, and then the scientists at NASA would take that picture, feed it through a computer, and the computer would measure the apparent magnitude of every one of those stars, or the brightest ones anyway, so that we have a measurement of the apparent magnitude of those stars every half an hour, 24 hours a day, for 4 years. These are basically the most studied stars ever. And if one of those stars dips for a few hours, we can catch it. Even if it doesn't dip by very much, we have the apparent magnitudes of those stars measured so well that if it dips by a little bit, we'll catch it. And so, after they got good at this, after the first couple of years, the software, the scientists, the computers, everything was humming along so well that they were able, using this method, to find very small dips, so that they were able to find a few planets that were as small as the moon. There are a few planets the size of Earth's moon orbiting around some of those stars, and they found them. And so, where are these planets? Everywhere. Here's a picture of the Kepler field. Here's after the first few years. Here's a dot for every planet that they found. It turns out, when this experiment started, they didn't know where they should be looking. Should we be looking for planets over in this area of the sky where there are more stars? Should we be looking for planets in this area of the sky where there are fewer stars? Should we be looking in the middle? They weren't sure exactly where they should be expecting to find planets. And the answer is everywhere. This part of the galaxy, this field, is filled with planets. And if this part of the galaxy is filled with planets, why not the rest of the galaxy? Maybe our galaxy is absolutely filled with planets. We just need to find them. Here's a graph of the size of the planets, because that's what the transit method measures, the size of the planets, versus the orbital period. This is the last big data release from the Kepler telescope in 2018. Or rather, the data was taken in 2017, and the data was published in 2018. 4,034 planets. were discovered. Most of the planets we've discovered have been with the Kepler telescope. And there are really big planets, planets that are 20 times the size of Earth, which is to say, about twice the size of Jupiter. Lots of planets that are the size of Earth, a few that are the size of Mars or Mercury, or these bottom few here are, the size of the moon. It's fantastic. But again, what kinds of planets are easiest to find? The big ones and the ones that are close to the stars with short periods. Small planets that are far from the stars, like Earth, they haven't found as many of. There's a reason why there's a big hole in the graph over here, and because this part of the graph is where there are small planets, like Earth, orbiting farther from the stars, so that you have periods of several hundred to 1,000 days. 20, 30 years ago, it was amazing to discover these exoplanets at all. The new cutting edge is to say, well, okay, we found lots of planets. Where are the Earths? Where are the Earth-like planets? Where are the planets the size of Earth that are, 1 AU from their stars? We haven't found as many of those yet. And the question is, have we not found as many of those planets because they're hard to find? Are they just the hard ones? Or do they not exist? This is why there are lots of different methods for finding these planets. Right? If all you have is the transit method, if the transit method is the only tool in your toolkit, then you're always going to have this hole in your data where the Earths should be. They found a few, right? There's a few planets like, these 4 around here. Maybe that fifth one there, if you want to say that, right? They found a few planets that might be like Earth, that are the size of Earth, that are the orbital distance of Earth. They found a few. Are planets like Earth exceedingly rare? Or are they just harder to find? I lean toward they're just harder to find. But if all you have is the transit method, it's going to look like planets like Earth are rare in the universe. This is why we have different methods. This is why we have the Doppler method, the coronagraph method. All of these different methods is to say, well, every method has its pros and its cons. Every method has its strengths and its weaknesses. Can we use some other method to fill in this part of the graph, to find more Earths if we assume they're out there? And you can kind of get it from this graph, or from this graph, right? This is a count of the number of planets found by Kepler versus their size, right? Planets like Earth are here, Neptune-sized planets are here, Jupiter-sized planets are here, the super Jupiters are here. Remember when we were talking about the nebular theory, right? The nebular theory would lead us to conclude that the smaller an object is, the more of them there should be. The bigger an object is, the fewer of them there should be. And that seems to be what we're finding with all these alien planets too, is that the rarest kinds of planets are the super Jupiters. And then the smaller planets, like Jupiter-sized planets, there are more of those. There are even more Neptune-sized planets, and there are even more... Oh, now it goes down again. If the nebular theory is right, then this graph should just keep on going, bigger and bigger and bigger, as you get to smaller and smaller planets. If the nebular theory holds true, the most common planets should be the smallest ones. And yet, as we go past the Neptune-sized ones, the smallest planets, we find fewer of them. Now, maybe the nebular theory is wrong. Maybe something about the way planets form means that Neptune-sized planets are the most common. Or maybe it's just that these smaller planets are the hardest ones to find. We don't know yet. Right? This is still an open question. You'd think, the simple answer is, oh yeah, there should be lots and lots of Earth-sized planets. Those are just harder to find. This graph, if we were able to find all the planets, this graph would be way up here. We don't know yet. This is still this is still a question people are trying to answer. Right? Can we fill in this part of the graph and find the missing Earth-sized planets? Can we do it using the transit method? Maybe. Or maybe there's a better way to fill in this graph using something else. That's what the future holds, right? For the past 20, 30 years, we were looking for planets using ground-based telescopes, and people are still using ground-based telescopes to look for exoplanets. The Hubble telescope, the Spitzer Space Telescope, and the Kepler, those are what we've been doing for the last 20 years. Right? The Hubble is still alive for a little while. It's going to be a few more minutes, or a few more minutes, a few more years. The Spitzer Space Telescope was it was a space telescope, kind of like the Hubble, except the Spitzer looked in the infrared. Spitzer was just recently shut down. The Kepler was also recently shut down. Kepler was alive and kicking for years, but in the last few years, things started breaking down, and they kept Kepler alive for as long as it can, but its mission is, for the most part, at its end. The TESS is the new big instrument. The TESS stands for the Transiting Exoplanet Survey Satellite. And so the TESS Space Telescope is it's a new space telescope looking for exoplanets using the transit method. And TESS has been online for about 2 years now, as of the time I record this video. And it's already found like 1,000 other planets. So TESS is going strong, doing great. Hopefully it has many years of its life left ahead of it. Trying to find more exoplanets. Hopefully maybe smaller ones. Hopefully ones, more Earth-sized ones. More Earth-sized planets farther from their stars. Hopefully TESS will be able to fill in some of the gaps, if there are any, assuming there are some, in the Kepler's discoveries. The next frontier is with the James Webb Space Telescope and WFIRST. The Webb and WFIRST are going to launch in the next few years here, and they are going to use the coronagraph. They're not going to use transiting, although they may catch a few transits, it's possible, but they're going to be designed to look for planets using the coronagraph. And we'll talk more about the coronagraph in the next lecture. So the Webb and the WFIRST are the future. The TESS is the near future. The Webb and the WFIRST are over the next several years, and then NASA and the other space agencies are starting to plan for the future of exoplanet hunts, to say, what telescopes have we not built yet? What telescopes can we build with next generation technology, next generation discoveries to find even more planets that we haven't found yet? Right? We've only been doing this for 30 years, but most of the planets discovered have been with the Kepler, and that was since 2009. And that was only in one, that was primarily in just one area of the sky. What does the rest of the sky look like? Where else are there planets in the galaxy? That's the exciting future ahead of us. So how do we find planets using the Doppler method? How do we find planets using the coronagraph? What does the past and the future hold? We'll talk about that next time. All right. Go ahead and hopefully this has helped you get the transit method homework done. By all means, if this didn't answer all of your questions on the transit method, bring those up in the live chats. Get that transit method homework done as soon as you can, and I will post the lab activity, which is an assessment on the transit and the Doppler methods, here shortly. So try to get that done in the next few days and get that submitted. All right. If you got questions, bring them to the live chats. Good luck. Hope everybody's doing all right. And on to the next lecture. All right. Take care, everybody.